All right, let's just dive right in. We see this symbol all the time, right? But have you ever really stopped and asked yourself, what is the square root of 2? I mean, really. It sounds so simple, but this one question kicks off an incredible mathematical detective story that takes us from ancient Greece all the way to modern computers. So let's unravel this thing. So, at its core, the definition is super simple. The square root of 2 is just the name we give to the number that, when you multiply it by itself, gives you exactly 2. That's all there is to it. But what is that number? Well, let's try to pin it down. We know 1 times 1 is 1. Okay, that's too small. And 2 times 2 is 4. Whoa, way too big. So this tells us our mystery number is lurking somewhere between 1 and 2. The question is, where exactly? To find our first real clue, we've got to do something a little different. We need to step away from just crunching numbers and actually look at shapes. Because it turns out this number isn't just some abstract idea. It's a real physical length you can literally see and measure. Yep, the ancient Greeks, who thought about math with their eyes and their hands, found the answer hiding in plain sight. It was inside the most basic shape you can imagine, a simple 1-by-1 square. This is where it gets really cool, where the number becomes real. If you draw a square where each side is 1 unit long, the good old Pythagorean theorem, a squared plus b squared equals c squared, tells us something amazing. We get 1 squared plus 1 squared equal the diagonal's length squared. That's just 1 plus 1, which is 2. So the diagonal's length squared is 2. That means its actual length is the square root of 2. It physically exists. It's not just a concept. Now, picture this. If you take that diagonal, treat it like the arm on a compass with the point at 0 and just swing it down onto a number line, bam, it lands on a very specific, very real spot. It's not a guess, it's a precise location. And now we know exactly where it lives, right there between 1.4 and 1.5. Okay, so we found it on the map. We know where it lives. But what if we want to write down its address, as a decimal? Well, this is where the endless chase for precision really begins. We can play that too big, too small game again, but let's zoom in. Let's try 1.4. You square that, you get 1.96. Ooh, so close, but still too small. All right, what about 1.5? You square that and get 2.25. Too big, so we've trapped it. We know for a fact now the square root of 2 is bigger than 1.4, but smaller than 1.5. You can see where this is going, right? We could keep doing this forever, trying 1.41, then 1.42, adding more and more decimal places. But it's slow, it's inefficient. It feels like we're just brute forcing it. There has got to be a better tool for the job. And there is. It's this fantastic little recipe. You can think of it like a number game. You start with any guess, let's say 1.5. Now, if your guess is too big, then 2 divided by your guess is going to be too small. So what do? You just average those two numbers, and that new average becomes your next much, much better guess. Then you just do it again. And just look at how ridiculously powerful this is. We start with our rough guess of 1.5. After just one step of dividing and averaging, we jump all the way to 141,666, which is already super close. You do it again, and you get a number that is astonishingly close to the real answer. This method just zeroes in on the value with incredible speed. And there are other really elegant ways to get close too. The square root of 2 can be written as this beautiful, infinitely repeating pattern called a continued fraction. It's like a fraction inside a fraction inside a fraction that just goes on forever. And every layer you calculate gets you an even more accurate fraction, getting closer and closer to the true value. So, we have all these amazing ways to get closer and closer and closer. But this leads us to the biggest, most profound question in our entire story. Can we ever just land on it? Could we find the one perfect fraction, some whole number divided by another whole number, that when you square it gives you exactly 2? It feels like we should be able to, doesn't it? So in math speak, a number that can be written as a fraction is called a rational number. And the key thing to remember here is that you can always boil any fraction down to its simplest form, where the top and bottom numbers don't share any factors. Like how 2/4 is really just 1/2. And here it is, the mind-bending reveal, a discovery that absolutely shocked the ancient Greeks. The answer is no, it is impossible. The square root of 2 can never, ever be written as a simple fraction. It is, in a word, irrational. So how can we be so absolutely sure? It's thanks to one of the most elegant arguments in all of mathematics, a proof by contradiction. The strategy is simple, even a little sneaky. We're going to pretend that the square root of 2 can be a fraction. And then we're just going to sit back and watch as that whole idea logically blows up in our face. Okay, stay with me here because this is the magic trick. We start by assuming the square root of 2 is a fraction, a over b in its simplest form. If we square both sides, we get 2 equals a squared over b squared. A little algebra, and you get a squared equals 2 times b squared. That tells us a squared has to be an even number. And if a squared is even, a itself must also be even. But hold on. If a is even, then a squared has to be divisible by 4. And if you look at our little equation, that forces b squared to be even, which means b must also be even. And there it is. That's the problem. If both a and b are even, our fraction wasn't in its simplest form to begin with. Our starting point led to a logical impossibility. The only way out, our original assumption had to be wrong all along. This wasn't a failure to find an answer. Not at all. It was the discovery that the number line was packed with an entirely new category of numbers that no one even knew existed. So let's bring it all home. What is the square root of 2? It's a real physical length, the diagonal of a square. It's a specific, exact point on the number line. It's a value we can chase and approximate with amazing accuracy using some clever tools. And most importantly, it's an irrational number, a member of a huge, strange, new family of numbers that can't be contained by simple fractions. So in the end, our little detective story has a happy ending. The ancient Greeks didn't fail. They succeeded in discovering that the mathematical universe was infinitely richer and more mysterious than they had ever conceived. And that leaves us with a final thought to chew on. The square root of 2 isn't alone. Numbers like pi, the golden ratio, the square roots of 3, 5, and 7, they're all irrational too. It makes you wonder, right? How many of these essential, impossible numbers are out there, quietly shaping the very fabric of our reality?